here we can talk a bit about hashing and what hashing is and how we use it to check quickly the content of files. So, because files can have too much content and that can be very large, it would be easy if I can take many bytes and I can assign a unique ID to those bytes. Okay, so I might want to take arbitrary input, a large an undefined size of input, but produce a defined size of output. I won't say that I'm going to take arbitrarily large files, but I'm only going to give you back a number that is, for example, 2 to the 128 bits long, or 64 bytes long, it doesn't matter. I'm going to give you back a fixed size number. Now, if the input that you give me is the same, I'm going to give the same output. However, if a good hash function would also have the property that if the input that you give me changes from the previous input that you gave me just slightly, then the number I'm going to give you is going to be vastly different. We can imagine that now we have taken a big space, a big domain that is the input domain to our function, and the output domain to our function is always kind of the same, right? We're only outputting numbers, for example, from 0 to the maximum 64 bit number that we said. So if we do that, there are guaranteed to be what's called collisions. There are going to be multiple inputs that you can give that will produce the same output. Now, a good hashing algorithm makes that pretty hard to find and pretty improbable, because we want to use hashing as some sort of, let's say, unique identifier, right? Although that's not always the case, and we shouldn't necessarily be thinking of hashing like that. But in reality, hashing is many times used kind of as a unique identifier. So if we have collisions in our hashing function, then that messes up our unique identification of the data. And I'm mentioning here two hashing algorithms, MD5 and SHA, the secure hashing algorithm. Okay, we're going to kind of look into how these guys are implemented in a very high level picture. So how is hashing used, and how is it used in real digital forensics cases? We have an example here. When, let's say that some person in court is accused of having a very incriminating file in their computer, and we say that they were in possession of that very incriminating file. Well, we don't really want to go in the details of that super incriminating file, right? We don't want to show it. We don't want to even touch it ourselves, right? But we can use this hashing property to say that, okay, the contents of this very bad file hash to the number 3457, for example, right? And because we hashed all the files on that computer, and we found a file that hashes into 3457, and we know that 3457 is a very bad file, this person should go to jail. Well, if you go there and you say, oh wait, I just found another file that can also have the number 3457, then kind of the previous argument just goes out of the window, and that person can now walk free, right? So if hashing is used in a way that it is tied to forensics, right, and forensic investigation, and we can create collisions for that hashing algorithm that make other files have the same hash as a very bad file, then we can imagine that the forensic value of that, the forensic value of our investigation is kind of lost. Now, the same way is the way that antivirus programs kind of work, right? Antivirus programs, you might download a file and they might say, oh, this file is malware, like I'm not allowing it to be on your computer. How do they know? Did they actually go through the file and reason about it? No, they have database of hashes. So when you download a file, they hash that file using that hashing algorithm, and then they say, oh, this file has a hash 2233, and I know 2233 is bad, so I'm not going to allow you to run it. Okay. Now, I'm listing here on the right side the Merkle, I'm sorry, I'm not sure I remember the exact name, Merkle-Damgard, I think, construction where the MD5 algorithm is using to actually produce a final number. I'm just going to kind of hint at how it works. So the MD5 algorithm is splitting the file in chunks, in blocks, and it's operating on every block individually, but in sequence. Okay, so it starts on the first block, and it has a hash algorithm, as we said, so it's eventually going to hash the first block. But it's not only hashing the first block, the contents of the first block, it's hashing the first block along with the hash of the previous block. Okay, let's think about it. On the first block, there is no previous block. So we put this thing called IV, initialization vector, here, which acts as a, placeholder for a first block. So we put this IV here, we hash it. That creates this, the hash of the IV. Then that gets packed with the contents of the first block, and that whole thing is hashed. And that produces a hash. That hash now goes here as the hash of the first block, and that's combined with the second block. It's combined with the data of the second block. So the hash of the previous block plus the contents of this block are combined and hashed, and that goes over here, and that produces a hash. So that hash with the contents of the next block are combined, and that produces blah blah blah, a hash, up until that produces a final number. Okay. This is kind of just a visual representation of how the MD5 algorithm kind of works. I'm showing you this here so that you kind of keep in mind that if I wanted to engineer collisions in this, the question is like, what do I need to control? Okay, one thing I can control is the IV, and this block, and that block, and that block, and that block, and all the blocks, right? So if I control all the blocks, I can produce the same file, right? So if I can produce the same file, then sure, I can produce the same hash. But what if I manage to control the output of, in this sequence, the output of the previous block and just one block? If I manage to also control that, these two, then I would also produce the same hash. And it doesn't really matter what was before here, right? Because if I kind of hijack that process, that sequence, then if I just hijack the hash of one block and the contents of the next block that these guys are combined, then I will still control what hash going to be produced. And that's kind of a hint on how we engineer collisions, on hashes. Now, doing some analysis here, and here I just have a screenshot that I'm showing you what I discussed before. Like, I have a file called evidence, and I can run the MD5 sum commands with just the MD5 sum. It gives me back a number, like 3A, C, B in hex. Then I add something to that evidence file, I do the same command, and then that number is vastly different. Okay, because that's what we talked about, those are the properties of hashing. So MD5 has 128 bits output, and let's say, is it secure? We can do some basic analysis. So the output is 2 to the 128. If we want to bring that in base 10 and make more sense of that number, we can think that 2 to the 10 is about 1024. So 2 to the 10 is 10 to the 3. Okay, approximately. So this can be 2 to the 10 to the 10. Okay, so that's 10 to the 3 to the 10. So that you can see how kind of 2 to the 128 becomes 10 to the 38, approximately. Now, I have given you a number here. It's probably outdated, but it doesn't matter. Just get an order of magnitude approximation. A modern GPU can test 200 million hashes per second. So here again, what am I trying to do? I'm trying to find two inputs that will produce the same hashing output. I'm just trying to brute force it, right? And I'm testing different outputs until I get, testing different inputs until I get the same output. And I find two different files that collide and produce the same hash. Okay, so I'm trying to brute force my way here. Okay, so a modern GPU can do 200 million hashes per second worth of tests, right? And that output space gives me 10 to the 38 total operations. Okay, well, I'm telling here like that's, if we divide that to the hash per second with our how many seconds that means, this gives me approximately 10 to the 22 years that I would need to kind of keep running until I find two files that share the same hash. Okay, now that kind of seems like a correct analysis, but it's completely not a correct analysis, because observe what I said. I said I want to find two files that have the same hash. Okay, so I'm now going to talk about the birthday paradox and an equivalent, let's say, statement of that problem, which it would be, let's say we're in a group of people and we want to find which of these people have the same birthday, right? Same thing. I have a group of files and I want to find which files have the same, which pair of files have the same hash. So here I'm rephrasing this. I'm saying, okay, let's say I'm in a group of people, right? And it has 23 people. What are the chances that two people share the same birthday? Now, just take a moment, think about it. You're in a party, there are 23 people around you. What are the chances that you share a birthday with someone else in that room? Well, intuitively you might think not a lot, but actually if you do the analysis, it's actually a 50% chance that two people have the same birthday. And to do that, you take all the k pairs, in this case k is 2, like you're going to find a pair of two people, right, in the group of n people, that n is 23, and you take the binomial coefficient here to find the number, you know, of pairs in that group. And if you want to find all the number of pairs in the group, you take the factorial of n, that would be 23 factorial, that's a giant number, right? 23 factorial divided by 2 factorial, that's 2, okay, 23 factorial divided by 2 times 23 minus 2, that's 21 factorial. So I have 23 factorial up here divided by 21 factorial down here. So 23 factorial is 1 times 2 times 3 times 4 blah 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 times 23. That's 1 times 2 times 3 times 4 blah blah blah, blah times 21. So we can take these factors out of the numerator and denominator, right? And I will only be left with 22 times 23 up here divided by 2. Well, if you do that, hope you get 2053, otherwise I've done a mistake. And if you get 2053 here, it means that 2053 is approximately the number of days in the year. So for these days in a year, it's quite probable that that in a group of 23 people, you'll find 2 people that share the same day in that year, right? 253 is here kind of the output size, right? And therefore, it's a 50% chance that you'll find some people having the same birthday in that size of a group. Now, another approximation you can use here is like if you take the square root of 253, it's going to give you like around 15 something, I think. And so you can also take the square root of the output size to find the number of these types of collisions that you might have. So in the previous case, you can take the square root of the output size, which is what was it, 120 bits, 2 to the 128, and that's going to give you an approximation of how often you'll find pairs of files that share the same hash. Okay, so just letting you know here, the analysis that we did here is wrong, right? That's why we write here bad analysis. Now, there are other types of, I kind of hinted at how you can use the Merkle-Damgard construction to engineer a collision, but there are other types of hashing functions, like the ones that are used on the SHA algorithm. And these types of functions are called sponges because they evidently can they can absorb entropy, and you can only squeeze them like as you squeeze a sponge to get the data out, only when they have enough entropy. I'm not going to claim that I understand the details of this algorithm because I'm not a cryptographer, but even on these types of vastly different algorithms that don't have like this chain property that we saw before, there have been collisions engineered, and you can check out this paper from Google that they actually managed to create different PDF files that have the same SHA output. Now, what do we do? Like, if we know that we need hashing to do our job in forensics, but hash algorithms can have collisions, then one simple trick that you can use is just use 2 different hashing algorithms and pack both hashes together. The probability for getting an attack on that is pretty low at this time, and that's what a lot of tools do that we're going to use. Now let's think a bit on what's happening when we do certain operations, what's happening on the hashes. So let's say we open a file, for example a JPEG file, and we open it with our favorite image viewer or image manipulation program. Let's say we open it with GIMP or Photoshop or whatever, and it's a PNG file, and then we save as, and we change the file type. We save it as actually a JPEG file, a completely different file type. Is it going to have the same hash or different hash? Think about it. Now, what if we add metadata on the file? These types of image files also have like metadata. You might be able to add like the resolution of the file there, right? That is listed, the resolution of the file. Or you might, certain metadata on image files can have like GPS coordinates that the image was taken at. What if I add metadata on that file? Will the hash of the file change? Yes or no? And then finally, what if I change the file name? let's say I have a food.png file and I make it bar.png file. Will that change the hash? Yes or no? Well, the answers of those, in the first one, when I actually change the file type, then yes, it is going to change the hash, because all the contents are completely different. The JPEG image has different representation on disk than a PNG image, so it has different bytes. It's going to be a different hash. But if I add metadata, then yes, if this metadata is part of the content, then it's still going to change the hash. If I change a file name, well, a file name is not really a part of the content of the file, so in that case it's not going to change the hash of the file. The file name is only something that's persisted in the file system that I have the file on, and only that part cares about the file. The contents remain the same. I'm showing you that over here, where I have a file called evidence that has a certain MD5 sum. I show you the MD5 sum here, and I copy the evidence to evidence 1. I'm running the MD5 sum again. It's the same hash. So the copy changes the modification, access, and change time, but of course it preserves the content, and therefore the hash is the same. I want to talk a bit about how to get data out of disks or other devices like USB drives, right? And I mentioned before that USB drives and other devices in Unix are shown like normal files on the system. Every device on your system in Unix is shown as a file presented under the /dev directory. So preserving the data on a USB, what does it mean? It means to preserve the data blocks, the actual content of the files on that USB stick, but also preserving the metadata, the file system level information on that USB stick. So when I want to image that source, I'm going to use a command called dd, and dd deals with devices, disk devices, and it takes certain parameters as what is the input file of the input device that I want, and what is the output file of where do I want the data to go to. And in this type that you use it, as I'm showing here, it reads all the contents of a device under /dev called sdb, and saves it to a file called /tmp/whole_flash.img. Now, I'm mentioning here this SDB name. On your system, it's probably going to be something completely different. Let's say you plug a USB disk on your system. The kernel is going to recognize that USB stick and it's going to give a device name to it. If you want to know what device name the kernel has given to it, you can look at the kernel messages when you do that action, when you plug the USB stick, and then the kernel is going to say, for example, oh, I gave it the name SDC, and SD traditionally in Linux would stand for SCSI disk. Doesn't matter, it's like a disk detected on a SCSI subsystem, and C because probably it's the third SCSI disk that it sees. And then if that USB stick also has partitions on it, we're going to talk more about that on the file system module, it's also going to assign numbers to every partition, like you're going to have SDC1, SDC2, SDC3, and so on for every partition. In the case you run it as we show here, this would copy the contents of the whole disk, all the partitions, not just one partition of it. So in this case, as I'm showing it here, it will copy the contents of the first partition, okay, in a file called /tmp/flash.img. Again, the way they use it is dd input file, and notice I'm not putting dashes in the dd command, so it doesn't accept the options with dashes as other commands I used before, ls for example. So the input file would be /dev/sdb1, and the output file would be /tmp/flash.img. Now, DD takes certain parameters, like for example block size. It can read data as one block, and every operation it's doing in one block's worth of bytes. In this case, I'm specifying the block size to be 512. I can specify the count, how many blocks I want it to do stuff on. I can specify the skip, if I want to skip certain blocks in the beginning of the file. So if I add all these guys together, it would be dd bs equals 512, count equals 4, skip equals 100. So that means, okay, I want you to use block size of 512, skip 100 first blocks that you see, so it's going to skip 512 times 100 bytes worth of blocks, and then count equals 4. I'm going to do 4 blocks after the ones you skipped. I want you to take these guys and maybe copy them to an output file if I have specified that. There is a video here. Again, obviously be very careful when you use the dd command, because you might actually manage to destroy your file system if that is also accessible on the computer you're doing that. Finally, I want to talk a bit about data carving. Using the dd command allows us to isolate certain parts of a stream of data, and that's very useful. So we can examine that part in an isolated fashion. So usually, to know the part of the stream that we want to extract, we want to know where it starts and where it ends. And by setting the block size and the skip and the count, you can see how you can specify a sub part of a stream of data that you want to extract, carve it out of a bigger part of data. This is very important in forensics, because very often we want to carve out something to work with, because we usually work with very large amounts of data and we just can't deal with the rest of the thing. We can only parse a smaller part of that system, so we want to take that part out, parse it, somehow deal with it while ignoring the rest. So that process is called data carving. So if we want to carve 4 megabytes of data out of a larger stream, starting at offset 512 kilobytes, we might say, okay, dd from that stream to carved bs 512k. Okay, I can specify like here kilobyte, megabyte, or whatever specifier. Then skip the first 512k, right? That makes sense here. And take 8 chunks worth of 512 each, so that would be 2 chunks is 1 megabyte, so 8 chunks would be 4 megabytes of data, right? Make sure you understand this. We're going to have similar assignments on the Dojo. So that's about it, guys. Thank you for following through this set of lectures. Again, here are some links. You can find very extensive documentation on using Linux and using these basic terminal commands in many places in the internet. We're just listing some videos here. You can find like the best thing you can use is the manual pages, honestly, for every command. Feel free to reach out on Discord for any questions you might have, and we'll see you on the next lecture. Have a great rest of your day.